Hello. So in this video, I am going to show how to use a Pitot Static tube to measure the flow rate in a duct. Okay, so the idea here is we have this duct here. It's carrying air and it's traveling forward at some velocity. The duct has a radius r, and in it is this thing called a Pitot Static tube. Um, it's called Pitot Static. This end is the pitot tube. This end is the static tube. Um, so together it's called the Pitot Static tube. Um, the idea of how it works is that air pushes in on this side because the air is flowing in, flowing this way. It pushes in this side, so it pushes the water level down here because air just flows across the top of this end of the tube. The flow rate of the air does not affect the pressure on this side of the tube. So it affects the pressure on the left side, but not the right side. That pushes down the water on the left, and therefore the water up on the right. You can look at the water level difference, and from the water level difference, you can infer the velocity and thereby the flow rate of the air through the pipe. Okay, so what we're going to do here is we are going to, I guess we'll start with, we will start with a using the Bernoulli's equation. So basically what we're going to do is we're going to compare 2 points. We'll do point 1 and point 2. So point 1 is inside inside the duct. It's got a velocity. The air is moving along with some velocity. The velocity of the air in the duct, and I'm going to assume the velocity is the same everywhere in the duct. So the air is flowing along, but then it flows into the tube and it has to stop. I mean, the water isn't moving, so the air, once it gets into the duct, eventually has to stop. Okay, so the velocity at 2 is 0. The velocity at 1 is whatever the velocity is in the duct. Okay, so we're going to use Bernoulli's equation to compare these 2 points to find the pressure difference. Okay, so Bernoulli's equation says that P1 plus 1/2 rho, and this will be rho of air, because air is the fluid we have moving, V1 squared plus rho air GH1 is equal to P2 plus 1/2 rho air V2 squared plus rho air GH2. Circle that there. Move that back over here. Okay, so when we compare these, the difference, you'll notice that when we look at 1 and 2, they have the same height, so we can kill those 2 terms. Also, the velocity at 2 is 0 because there's no velocity. This air isn't moving once it gets into the pitot tube. Okay, so we can solve for P2 minus P1. So move this P1 over to the other side, and we find that's equal to 1/2 rho of air V1 squared. Okay, so that tells you the relationship between the pressure difference and the velocity of the air. Okay, now the way we're going to measure that pressure difference is with the fluid levels. Okay, so you may remember that the pressure is this, because it's not moving, the pressure is the same at all points that are horizontal level in a fluid. So this point is the same pressure as that point. So when we look for the pressure difference between this tube and this tube, basically it comes from the fact that on this side there's extra water, pushing this side up, whereas this other side just has air. So we have air on this side, water on this side, so the pressure needs to be bigger here to hold the water down. And the amount needs to be P2 minus P1. I should note that P1, the pressure 1 here, is the same as the pressure on this side. This is because as the air flows across the top of the tube, it doesn't do the whole Bernoulli's thing where it pushes into the tube. So the pressure, so basically the static end of the tube is just measuring pressure. It's just got an open-ended tube there. The air pressure in this, say right here, is basically the same as it is out here. Okay. So there's that. So when we say P2 minus P1, basically we're measuring the pressure here versus the pressure here. And the difference is this side has a stack of water, this side has a stack of air. So the pressure difference is rho g h, like we've talked of, like, you know, pressure differences as you go down in fluid. Technically speaking, it should be rho of water minus rho of air times GH. However, this rho of air is really small. We'll talk about that. You know, let's just do that right now. So rho of water, if you look up the density of water, it's about 1,000 kilograms per cubic meter. Rho of air is something like 1.2 kilograms per cubic meter. So rho of water minus rho of air is like 998.8 kilograms per cubic meter, which is effectively 1,000. You know, at least to like two significant digits, maybe two significant digits. It's basically 1,000. You know, rho of water so much bigger than rho of air, we can more or less just ignore that as small. Okay, so our pressure difference is basically rho water GH, basically the height difference in the water. But the H there is delta Y. Right? The height difference on the two sides is delta Y. Okay, so now we can just equate these two sides here. So we can get 1/2 rho air V1 squared is equal to rho water G delta Y. Okay, we can then solve for V1. We're trying to find the velocity of air in the duct. V1 squared is equal to rho water G delta Y times 2 over rho air. We can then take the square root of both sides, so we get V1 is equal to the square root of 2 rho water G delta Y over rho air. Okay, so we're doing real good. We've got the velocity of air in the duct. Assuming that the velocity that we're measuring is the average velocity, you know, air is moving more or less like plug flow through the pipe, or through the duct, that's a reasonable approximation. Then we can say that the flow rate, Q of air, is roughly equal to V times V1 times area of the pipe. Where area of the pipe, if we are told it's a round pipe and has a radius r, is pi r squared. So area of a circle. Okay, so we put those together and we get the flow rate is equal to pi r squared times V1, which is the square root of 2 rho water G delta Y over rho air. And that is how you use a pitot static tube to measure flow rate. So this equation right here is how you use it to get velocity, which is a lot of times what pitot static tubes are used to get. If you want to convert that into flow rate, that's the answer down there. Okay, and that concludes